So the next speaker is Jinshan. He's from School of Computer Science and Engineering, Nanjing University of Science and Technology in China. Jinshan is actually also an older friend of mine. So we have worked together a long time ago. Right now he's a professor of the School of Computer Science and Engineering, Nanjing University of Science and Technology. He received his PhD in computational mathematics from Dalian University of Technology, and also a joint training PhD in UC Merced. So his research interests include low-level computer vision, image video restoration, enhancement, and related problems. He's area chair of CVPR 2022. Today, he's gonna talk about deep image video restoration networks. So, Jinshan, I'm gonna hand it over to you right now.
Okay. Thanks for the Dr. Wang's introduction, and also thanks Professor Li's invitation. It is a great honor to share our work here. And in this talk, I will introduce our work about how to explore the knowledge of image degradation to constrain the deep neural networks for better image restoration. The classical image restoration problems include the image deblurring, image dehazing, image superresolution, image dehazing, and so on. So the goals of these problems are to restore the clear images from the gateway input. And we know that these problems can be usually formulated by this image degradation model, where B denotes the degraded image, and I denotes the latent clear image. F denotes the degradation mapping function, and N denotes the image noise. For example, if we take the image deblurring as an example and assume that the blur is uniform, the degradation process can be formulated by this linear convolution model, where the blurred image is usually modeled as the convolution of a sharp image with a blur kernel and plus noise. And here we use the star, denotes the convolution operator. For image deblurring, I think Professor Li will give more details about the blur, especially for the defocus blur. And he also has done lots of great works in image deblurring. And many our deblurring works are mainly motivated by his researches. So for image deblurring, and we know that it is quite challenging because we only know the single blurred image and don't know the sharp image, blur kernel, and noise. So similarly, in image dehazing, we can use this linear model to describe the haze process. And this problem is also ill-posed as we only know this haze image and don't know the clear image, transmission map, and atmospheric light. So generally speaking, the image restoration problem is ill-posed, which usually contains many possible solutions. For example, in blind image deblurring, we can find many solutions that satisfy the blur model. And therefore, the task of blind image deblurring is to find this group of solutions. So to solve this problem, most conventional methods usually take a probabilistic approach. And here we take image deblurring as an example. The probabilistic approach usually models the posterior distributions of a latent clear image and blur kernel given the blurred image. And this term can be decomposed into the likelihood term prior on the latent image and block kernel. So based on this approach, we need to model the properties of the latent clear image, degradation factors in the degradation mapping function F. For example, the block kernels in blind image deep learning and the image noise. So most conventional image deep learning methods mainly focus on designing effective image priors to solve image deep learning. And during the past several decades, they have made significant great efforts to design effective image priors to solve image restoration problems. And this slide is from Michael Elliott, which gives the evolutions of the image priors. And I think we are familiar with this evolution of the image priors. For example, the energy-based ones and the widely used total variations, sparse coding, and so on. And we also have witnessed that the key success of the conventional methods mainly stems from designing kinds of effective image priors. So with the defined image priors, we can use it to better constrain the solution space to obtain high quality clear images. We know that the prior-based approach is able to generate physically sound results because it is based on a clear physics model. And in addition, this approach usually have a good generalization ability compared to some data-driven approaches. But these methods also have some limitations. The handcrafted priors are based on the statistical observations, which may not model the inherent properties of the clear image, and thus lead to unsatisfactory results. For example, in this case of image deep learning, if the priors for the latent clear images are not defined well, and we can't effectively restore a clear image with the fine details. Another problem is that as the priors are designed more and more complex, the corresponding optimization problems becomes more complicated, which are difficult to solve. And this significantly limits the real applications of these prior-based methods, for example, on smartphones. And in recent years, deep learning has been applied to image restoration and provides an effective way to solve this problem. It plays a dominant role in recent restoration tasks. These methods greatly simplify the problem of formulation, where we only need to prepare the training data and design networks to directly estimate the clear images from the degraded image. So compared with the prior-based approach, we don't need to model the properties of the degradation factors, latent clear images, and so on. And we have also witnessed significant progress in image restoration due to the use of kind of deep neural networks. And here are listed the evolutions of the deep neural networks for image super resolution and based on this survey paper. And we can see that the network designs become more and more complicated. And some key components in these networks, for example, the channel attention, are borrowed from high-level learning tasks, which do not consider the degradation process. And in addition, based on the conclusions of this survey paper, the networks contains more and more network parameters. So like this figure, which may lead to the limited generalization ability. And to summarize, the deep learning-based methods have some merits as mentioned before. For example, they greatly simplify the problem formulation because we don't need to design prior on the degradation factors, latent clear images, and so on. In addition, due to the better representation ability of deep learning, the deep learning-based methods usually have a better representation ability on modeling the properties of the clear images, and thus generating high-quality clear images. However, based on the aforementioned survey paper, the limitations of the deep learning-based methods are also obvious. And the first one is that the designed networks are more complicated blind black boxes. And we should know that this is a generic limitation of the deep learning-based methods, which is not limited to the image restoration tasks. Due to this limitation, the performance gains are mainly due to the use of large capacity models in some restoration tasks. And in addition, if the networks contain more parameters, it will increase the difficulty of the training process. And the trained deep models are likely to overfit in image restoration. For example, when we use deep learning to solve image restoration, the networks trained on the dataset 1 may not generalize well on the dataset 2 for the same task. And in addition, the generalization ability on the real-world application is not good compared to the handcrafted prior-based methods. As in this case, for blind image deep learning, the deep learning-based methods do not always perform better than the handcrafted prior-based methods. So since both the prior-based approach and the deep learning-based ones have advantages and limitations, it is of great interest to keep their advantages and avoid their limitations. And our motivation is that whether can we explore the knowledge of the image restoration to guide the deep neural networks instead of simply increasing the network parameters to overcome the limitations of most deep learning-based methods for better image restoration. So based on this motivation, I will introduce how to explore the physics model and the domain knowledge to better constrain the deep neural networks for image and video restoration. So now let me first introduce our work on how to explore the physics models to constrain the deep neural networks for image restoration. I will start from the GAN models. Since the GAN has been proposed, it is widely applied to many varying tasks. In image restoration, it is applied to image super resolution, image deraying, image deblurring, image dehazing, and so on. And we also note that these methods share the similar network designs, but achieve amazing results compared to the prior-based methods. So a question is that, does the GAN-based methods really solve the image restoration problems well? So the answer is no. If we carefully analyze the GAN-based methods for image restoration, for example, in image dehazing, although it is able to remove haze from this haze input, but it also introduced artifacts. And we also found that these artifacts usually lead to the results that do not satisfy the degradation model well. However, for the prior-based approach, they do not introduce the artifacts. One main reason is that they require the generated clear image satisfy the degradation process during the optimization process. However, they do not effectively remove the haze, because the hand-crafted prior may not model the inherent properties of the clear images well. So one question is that, can we explore the properties of the prior-based approach to constrain the GAN-based methods to overcome its limitations for image restoration? So based on this motivation, we developed a physics GAN framework where it introduced the constraint from the degradation process. And here is the model of our physics GAN framework. And the first part is the commonly used GAN model for image restoration. The second part, it denotes the constraint from the degradation process. And this equation also demonstrates that we do not only require the generated image satisfy the degradation model, but also require that the regenerated image has the similar distributions to the degraded input. And here is the overview of our methods on uniform image deblurring problem. During the training, the proposed methods include the forward stage and the backward stage. The forward stage is the conventional GAN model that is widely used for image restoration. And the backward stage is used to impose the generated results, for example, J or B, to satisfy the degradation model. And when the proposed model is trained, we can use the forward stage to directly estimate the clear image, for example, G or B, from the degraded input. And thus, the backward stage is only used to constrain the network training. As our method is based on the supervised learning approach, we apply the same degradation factors, for example, the block kernels that are used to synthesize the training data in the backward stage. Next, I will show some results to demonstrate the effectiveness of the proposed methods. And here is the applications on the real captured text image deblurring. And we know that the GAN-based methods is based on the feed-forward model to estimate the clear images from the blurry ones. And we can see that it does not effectively remove the blur from this blurry image. And in contrast to the GAN-based methods, our proposed method involves a backward stage that uses the physics model to constrain the network training, which thus obtains much clearer image, and the characters are much more clearer. So for image deblurring and related restoration tasks, one may ask whether the contents of the generated image are reliable or not. Because we all know that the GAN-based methods usually generate fake contents. To answer this question, we use the OCR accuracy as the evaluation matrix. And we can see that the GAN-based methods generate the results with the lower OCR accuracy values than the SIN-based methods. And this further demonstrates that the GAN-based methods introduce the fake contents during the restoration process. And in contrast, the OCR accuracy is improved significantly by exploring the physics model in the GAN framework. And here is the application on face image deblurring. Other methods usually fail to generate reliable results. And in contrast, our methods still obtains much clearer face image. We further demonstrated the effectiveness of our methods on image delaying and compare it with the GAN-based methods. And we can see that exploring the physical model in the GAN framework is able to remove rain. And here is the application on image dehazing. And we know that the pix-to-pix method is based on the conditional GAN model. And we can see that it generated the results with significant artifacts and color distortions. And in contrast, our method is able to remove such artifacts and obtains much clearer image. The above-mentioned methods explore the physics model in the intensity space. And we know that most deep neural networks perform in feature space. Therefore, we further extend this work into deep feature space and develop a feature dehazing unit based on the haze model. So for image dehazing, and we can use this physics model to describe the haze process as mentioned before. And based on this physics model, we can estimate the clear image by this equation. If we apply a deep feature extractor F to this equation, and we can get this model in the deep feature space. And here F denotes the deep feature extractor. And with further some mathematical derivations, we can finally get this model. So based on this model, we develop a feature dehazing unit to estimate these two components and use these two components to estimate the clear features Fi so that we can use the clear features to better help the clear image reconstruction. And finally, we embedded the feature dehazing unit into a deep convolutional neural network with an encoder and decoder network architecture to solve the image dehazing problem. And we also demonstrated the effectiveness of the proposed feature dehazing unit. And we can see that using the proposed feature dehazing unit is able to help image dehazing. Next, I will introduce how to explore the domain knowledge of videos to constrain the deep neural networks for video restoration. So for video deblurring, the blurred frames are the integration of the clear frames along the trajectories during the explore time. And this physics model is first proposed by Dr. Cho, Professor Lee, and Dr. Wang from their Asiagraphics work. And we can see that this is an ill-posed problem because we only know the blurry video and don't know the trajectories H and the clear videos I. So to solve this problem, conventional methods usually explore kinds of image priors to restore clear videos. As mentioned before, these methods also have a better generalization ability, but the image priors usually lead to complex optimization problems, which are difficult to solve. The other main critical problem is that these methods are usually sensitive to the motion blur estimation. If the restored intermediate latent video contains small errors, they will significantly affect the following motion blur estimation. So to solve this problem, most existing deep learning-based methods usually develop end-to-end trainable networks to solve this problem. And we also know that these methods also achieve state-of-the-art performance on kinds of benchmark data sets. However, as mentioned before, most of them, the performance gains of the most deep learning-based methods are mainly due to the use of large capacity models. In addition, although decent performance has been achieved on the synthetic datasets, they do not perform well on the real-world applications. And in machine learning, we know that although using more parameters will reduce the training error, but the trained models are likely to overfit. And here we give an example to illustrate this problem. And this example also shows that existing deep learning-based video deep learning methods do not perform well on the real-world applications. And we can see that they do not effectively remove the blur. In addition, we further note that most existing deep learning-based methods estimate the alignment information from the blurry input. However, based on the blur process of the video, the alignment information is related to the clear frames instead of the blurry ones. And thus, these methods do not follow the degradation process well. And to overcome these problems and design a compact model for video deep learning, we estimate optical flow from the intermediate latent frames. Motivated by the alternative minimization methods that is used in conventional video deep learning approach, we develop a new cascaded inference approach to iteratively update the optical flow and the latent frames. And in addition, we also note that in a video, not all the frames are blurry. We can explore these clear regions or subpixels to help video deep learning. And one effective method is the temporal sharpness per hour, which is first proposed by Dr. Cho, Professor Lee, and Dr. Wang. For example, we can use more adjacent frames to choose the subpixels based on the temporal sharpness per hour. And the temporal sharpness per hour is defined based on this equation. And in addition, we can also use the patch matching methods to select the clear regions for better image restoration. And here is the overview of our framework. And we can embed the temporal sharpness per hour into an end-to-end trainable network and develop the cascaded training method to solve the video deep learning problem. We also demonstrate the effectiveness of the cascaded training. The results show that without using cascaded training, it's not able to remove the blur well. So like this figure. While using the cascaded training methods, obtains much clearer frames, but the network parameters are still the same as this baseline method. And we also know that as the proposed cascaded inference involves several stages, we further examine the effect of the number of the stages. We can see that using more stages can improve the performance. However, the improvement is not significant when using more than 2 stages. And thus, we use 2 stages in our methods, considering both the efficiency and the effectiveness. And here we show the effectiveness of the temporal sharpness per hour on video deep learning. And we can see that the proposed methods obtains clearer images due to the use of temporal sharpness per hour. And in addition, using the temporal sharpness per hour does not increase the model parameters. And here are some comparisons. And we can see that our method is able to generate a much clearer image with the fine detailed structures, and other evaluated methods do not effectively remove the blur. And here are another comparisons. And we can see that our methods obtains much clearer frames with clearer structures and characters. And we also show the video deblurring results on real captured blurry videos. Our methods obtains much clearer videos than the evaluated methods. This is a video deblurring results. Okay, to summarize, we saw how to explore the physics model and domain knowledge to better constrain the deep neural networks for image and video restoration. And we can better understand the relations between the deep neural networks and the image restoration tasks and derive new network architectures for image restoration. Okay, that's all. Thank you.
Thank you, Jinshan.
Okay, thank you.
So, yeah, so I'm not sure how many people are online, but if you have questions, you can post in the chat window. I can start with one question. Can you go back to slide 22? I think that's a
22.
That's a main equation for the physics-based model.
This one.
Yeah. I'm just trying to understand because you went a little bit fast. I just want to go back one, like 22, the equation.
This one.
Okay, so for the physics model constraint, so for deblurring, you need the blur kernel here, right?
Yes.
So basically, it can only be trained with synthetic data. Is that right?
Yes.
Okay. What is DG and DH?
Okay. The DJ is used to let me see. So the DJ is defined based on this equation. It is used to distinguish whether the generated image J or B have the clear distribution, has the clear properties or not. It is based on the standard discriminator.
Mm-hmm.
And the DH is used to distinguish whether the regenerated image, so the J or B will be replaced by F or J or B. And this one, D or I, this I will be replaced the degraded input.
Mm-hmm. Okay. Okay. Yeah, it's a it's a little bit. It takes a little bit time to digest this equation. But what? But this okay. It's conventional GAN plus. So how do you determine the alpha here? It's just a fixed parameter. The weight.
Yes, the alpha is determined empirically based on the experimental results. So we don't have any theoretical results on this value. It is just based on the experimental results.
Mm-hmm.
So I also found that when people ask how to about the block kernel in the test stage, so in the information.
I'm sorry. So there's a question.
I just saw one question in our
right.
Zoom
so
information
from YouTube, for the physics scan model on image deblurring, what if we do not have the blur kernel at test time?
Oh, okay. Maybe I will introduce the framework of our methods, because in the training stage we use the blur kernels, but at the test stage we only use the feed forward models and don't use the feedback stage during the test stage, because the feedback stage only used to constrain the network training. After the network is trained, we do not need the blur kernels in the test stage. I think,
right.
Yeah.
That's true. Yeah, I agree. So I guess another question I have is, so here for image deblurring, you have a physics-based model, but actually for video deblurring, you can still derive a physics-based model, right? Because video, we know how video, the blurring video is caused by camera move, by camera shake. So, but in the second work, you use a kind of domain knowledge-based approach. Is that because the physics model is kind of a little bit too hard to describe or something like that?
Yes, because the physics model, we just motivated from the degradation process and don't use the physics model in the video deblurring problems, because it is hard to solve this problem in the deep learning based methods. And for the domain knowledge, we use the temporal sharpness prior, which is proposed by your Asiagraphics work.
Right.
So the physics model mainly motivated our method like this one, because we found that based on the degradation process, the alignment information should be related to the clear frames instead of the blurry ones. But most existing deep learning based methods usually estimate the alignment information, for example, the optical flow information or the offset based on the deformal convolution. And these offset are all estimated from the blur input. And I think these approaches will not generate physically sound results.
Okay. All right, so if there's no more questions, let's thank Dr. Pan and switch to Dr. Lee. Senyong, are you ready?
Yeah, let me try to share my screen again.
Okay.
Okay, I will stop.
Jinshan, you can stop sharing now.
Thank you.
Thank you.